Okay, I have 7:34 and a half, so I think we'll call the meeting to order. Jeff, sit down. Come on. Okay, thanks everybody for joining us tonight in person and online. My name's Clayton Knoll. I'm the current president, and I'm glad everybody could join us tonight. Now, before we get started, I got a report just recently from the SETI Institute, and they have now discovered why aliens are not coming to our solar system. They said they read the review and we only got 1 star. I know it's a dad joke. Come on. My 7-year-old grandson told me that joke. So I figured, okay, appropriate to a certain degree. Okay, so we'll start off with the January 13th meeting minutes. They're on the members area of our website, and it's I'm going to ask if there's any errors or omissions. Okay, not seeing any. We'll get our secretary then to make the motion to have the minutes accepted.
I move that the
gotta find our secretary's not here tonight. Are you online,
Can you hear
Tom?
me? Can you hear me?
Oh, there you are. Can you make that motion?
I'll make the motion. I move that the minutes of the regular meeting of January 13th, 2025 be approved.
Do I have a seconder? Dennis in the back. Thank you. Okay.
Who was that?
Did you get
Danny
that?
Boucher. Okay, thank you.
Okay, you got it. Okay. Do we have any questions? Nope. Okay. Call for the vote. All in favor of accepting the minutes posted?
Aye.
Okay. Opposed? Seeing none, motion is carried. Okay. So we have a guest speaker tonight, and I am going to have Sharon Morsink who will introduce us for us.
Thank you very much. I'm very happy to introduce today's speaker, Margaret Ridder. I first met her in 2019, so about 6 years ago, when she started her master's degree at the University of Alberta. She's now in the final year of her PhD. She's working with Dr. Craig Heinke, and she's studying white dwarf stars and I guess which can be in cataclysmic variables. And we're going to be learning a lot more about that tonight. She's an expert on observing them with radio telescopes. So come on up.
I have a fancy screen.
Right, you don't use this one. Get this one up. I'll give this to Frank. All right, does that work? Oh,
It's a bit, I'll try not to yell. I'm not used to hearing my own voice in the all the presentations I've given before. I just yell and gesticulate in front of a screen. Okay, so tonight I'm going to be going over a little bit about my research, and before that, all of the necessary prerequisites. So hopefully there will be a little bit of everything in here for everyone. We'll start out talking a little bit about what cataclysmic variables are. That is a white dwarf and a red dwarf star orbiting each other in a binary. And to begin, we need to know, how do you get those two things? So I'll start off with a hopefully rather familiar topic to a lot of you, main sequence stars. So here, maybe a familiar diagram. This is the HR or Hertzsprung-Russell diagram. On the x-axis, we have temperature. So things that are red are going to be very cold, and things that are blue are going to be very hot. And on the y-axis, we have brightness. So dim things are near the bottom, and very, very bright things are near the top. And round about the middle, you might be able to see this line. This is the main sequence. So this is where every star begins its life. They all start fusing hydrogen right here. This goes for stars like our sun, things like Sirius B, I think it's Sirius A or Sirius B. I'm not a real astronomer. I don't know how these things work. There. Timer. Don't want to go over time. So, round about the middle here. Oh, do I have a laser pointer? I do. Oh, this is great. So here is round about where our sun is. And the other kinds of stars that we're going to be talking about are down here. These are red dwarf stars. So things that are very, very cold and very, very small. They're only a fraction of the size of our sun. And because they're so small and so cold, only a few of them have started to evolve off the main sequence. So started becoming older stars, not just having a nice pure core of hydrogen, but moving away from the main sequence itself. Now, the sun-like stars, they don't stick around for very long. They live for about 10 billion years on the main sequence before they run out of hydrogen in their cores and they start to fuse helium. And then they work up the chain of elements, going from helium to carbon and oxygen, and then they all end up somewhere down here. This is the white dwarf land. So we'll talk a little bit about how we get there, because this whole process is very non-intuitive, this little line I've drawn on the HR diagram. But this is what's going on the inside of the sun. So to begin, the main principle that I want you to understand is how equilibrium works. So stars are constantly fighting to hold themselves up. Gravity wants to collapse the star, it wants to push it down, and radiation pressure, that is the pressure from the photons that are being generated inside the core via nuclear fusion, are pushing out against gravity. So for most of their lives, while they're fusing elements in their cores, they're in a bit of a balance. So gravity pushes in, nuclear burning provides a pressure going out. So right about now, what the sun is doing is it's fusing hydrogen. It hasn't really evolved off the main sequence yet, just a teeny tiny bit. So in this diagram that I have over here, you'll see my toy sun. It is definitely not to scale. This circle that I've drawn here for where the core should be is, it would be, let's see, how big would the sun need to be if the circle was this size? It'd probably be many, many times the size of the Telus World of Science. So this red letter is just going to be fusing hydrogen. Anything that's red is going to be fusing. Anything that's written in black is just going to be hanging out. So right now, the sun is fusing hydrogen ions, that is protons, together, and you just need about 4 of them to make a helium atom and a couple neutrinos. We won't be talking about neutrinos. Don't worry about them. They're very cool. Lots of astronomy can be done with neutrinos, but we don't need to worry about it today. Eventually, the sun is going to run out of the hydrogen in its core. It's going to use it all up and make it into helium. And then it leaves behind an inert helium core. So inert just means that it's not fusing anything. It's just sitting there. And so then there's no more radiation pressure to hold the sun up. So the core begins to collapse a little bit, and that raises the temperature to the point where it starts to burn helium. Now the rest of the star also heats up, becomes a little bit more puffy, and out in a shell, it burns hydrogen as well. So we end up with a kind of onion type star. Now, eventually, of course, that core is going to run out of its helium supply, and it's going to leave behind an inert carbon and oxygen core. And for a little bit of time, we'll still have some fusion out in the outer layers of the sun. But these things are very diffuse. They're very, very puffy. And because of that, the stuff that's out near the edge of the sun at this point, so this is going to be in about 4 billion years, 4.5-ish from now, that stuff near the edge is very loosely bound to the center of the star. And so any little itty-bitty push can liberate it from the sun. And this happens all the time in other sun-like stars, and they leave behind these beautiful things called planetary nebulae. So now that James Webb is up in the sky, it is obligatory for every astronomy talk to have a James Webb Space Telescope picture. So here is my tithing, I guess is the word for it. But here, you can see there's this wonderful ring of material that all used to be part of the star. But around about the center, it's going to leave behind a little skeleton, that carbon and oxygen core. Now, before we get back to all the physics stuff, I do want to show you one more, because I thought this was wonderful. This is the Butterfly Nebula. And you'll notice that it's a bit different. So around the center there's this kind of lynching going on. There's a bit of gas and dust that's preventing all of the stuff that's coming off of the star in this case, and making it go out in a conical, like an hourglass sort of shape. Oh, okay. So that thing left behind, the little hot skeleton, is the carbon and oxygen core. That is a white dwarf. That's all it is. It's just a leftover junk from a thing that used to be a star. So before we continue on about cataclysmic variables, I want to take a little interlude and just give you a bit of information on them, because by themselves, they're very cool. So a white dwarf is very, very small, about the size of the Earth, but it weighs about the same amount as the sun. So this stuff is very dense. This is Sirius. This is its little friend. That is a white dwarf. Not this wonderful thing right here. This is a big, hot blue star. This is its tiny little white dwarf friend. So these things are mostly made of carbon and oxygen, although there's some other kinds where you can have a little bit of magnesium and neon, but for the most part, carbon and oxygen is what you're going to get. So these things are not fusing elements. That's one of the things that I think people often get confused about when they hear about white dwarfs. So because normal stars are actually fusing elements, this thing is not doing that anymore. It is the leftover stuff from a sun-like star. So gravity's still trying to compress it, but rather than being held up by radiation pressure, it's being held up by this strange thing called electron degeneracy pressure, which is a principle of electrons that they hate their neighbor. They do not want to be close to them at all. They want to move as far away as possible from their little electron neighbor, but soon enough they're going to hit another one, and so they have to move back in the other direction. So they're just stuck there trying to stay as far away from each other as possible. And they will do that for a few billion years until they cool off and become interstellar lumps of coal. So they're kind of boring on their own for the most part, but they provide a wonderful laboratory for physics as long as you combine them with another star. And that is what I like to study. So these are cataclysmic variables. So when I say interacting and an interacting body, what I'm talking about is this. So we have our little red dwarf donor star over here, and we have a white dwarf accretor. So donor, accretor. And because the donor star has just started to evolve, it's just getting a little bit puffy, it's starting to spill itself over onto the white dwarf. So this thing right here is an accretion disk, and there's all sorts of accretion disks in the world. There's accretion disks that make the solar system. There's accretion disks that power supermassive black holes at the centers of entire galaxies. Accretion is very important. Accretion makes everything. And it really is just stuff falling onto other stuff. Just that process is everywhere. So it'll make planets, it'll make stars, it'll make black holes bigger and bigger. It works for neutron stars and it works for white dwarfs too. So I want to take a little sidestep here to talk about what these things actually look like. So this is one particular I don't want to talk about jargon today. This is one particular cataclysmic variable called SS sig. And because of that accretion process, and because it has a little disk, it goes through these wonderful things called outbursts. And outbursts are just an increase in the amount of stuff falling onto the white dwarf, and it gets much, much, much brighter, the whole system. So as you can see here, we start off very, very dim, and we have a rapid increase, a plateau, and a slow decline over the course of about a month. And this kind of process is very repeatable. You can see it every few months. SS Sig is very wonderful, given that it's bright enough to observe with backyard equipment. So if you just have a regular old 6-inch or even an 8-inch telescope, you can go and observe these things in your backyard. That's one of the nice things about this sort of stuff, is that they're so easily observable because there's so many of them and we've known about them for a while. Now, you may be wondering where I got this data from. This is the AAVSO, or American Association of Variable Star Observers, and they provide some of the most useful alerts for astronomers because we want to know when things like SS Sig go into outbursts. We want to be able to explore that physics. And we also want to know when they're not in outbursts, because there's different kinds of physics that we can explore. And so basically all that is to say that monitoring is very important, and amateur astronomers play a key role in that monitoring, because I'm one of those people who wants things to not be super duper bright. I want to look at cataclysmic variables when they're rather dim, because all that accretion business can wash out the kinds of emission, the kinds of photons that I want to observe. All right. That's where the radio emission that I want to observe is most visible. So, before we talk about how we observe cataclysmic variables, and, my favorite object, because it's the one I observed, astronomers all have their favorites, and I'm going to talk about my favorite today. But first, we're going to talk about radio observations, because radio observations are pretty cool. They're a little bit weird in comparison to optical telescopes, but they're weird in a wonderful way. So, the main limitation of radio astronomy is the physical size of an antenna. So with something like Hubble, you can reach, arc-second resolution. That's very easy. You can reach arc-second resolution with a lot of stuff here on the ground. So very, very fine detail. If you wanted to see stuff in the same amount of detail with a radio telescope, you would need a dish sort of like this at Green Bank that was kilometers in size, something about the size of Edmonton in reality. And this right here, the Green Bank telescope, which is 100 meters wide, this is me for scale, standing about 30 meters away from the thing. This will get you a little bit of resolution. This is for people who study big gas clouds and stuff. I study tiny things. This is not good for that. So if you want to observe very small stuff on the sky, what you have to do is fake having a larger mirror. So you can say, oh, well, what if we have this big old area? We want to make a nice big 40-kilometer mirror, but we don't have enough stuff to build the mirror, so we're just going to put a little piece here and another piece here and another piece over here and sort of fill it in as much as we can, because we don't have enough material to build that sort of thing. That is the basis of interferometry. You're faking having a much larger mirror than you really do. And so, basically, by the way, this is pictures of the VLA from Rick Bram. He said I was allowed to use these, and I'm very happy because they're beautiful. And it illustrates exactly what I want to show you. So this is one of the VLA's dishes. This is about 25 meters wide. And depending on where the dishes are, you can sort of move them around. They can be from 0.6 to 36 kilometers away from each other. And they move by having people get in little trucks and then move them down these little Y-shaped arms, so they can be really compact, fake a smaller mirror, and then they can be really spread out, so faking the biggest mirror that they can. And to give you an idea about, how old this thing is, it was built in the 1970s. The VLA is a fantastic facility that I use, and because it was recently updated, and when I say recent, I mean 2012, because it was recently updated with these nice big receivers, they cover large ranges of frequency such that you can sort of, well, you don't have to exactly know where to look to be able to find some of the cool physics that you need. You can just use a nice big frequency bucket and then say, well, what is out there? And of course, because I am a radio astronomer, I have to shamelessly plug the next generation VLA. It will be centered roughly where the current VLA is and spread all across the North American continent, even out into Hawaii. So it's going to be one of the biggest and best of the radio interferometers next to the square kilometer array, which Canada is involved in. Oh, and before I move on, no, you cannot plug headphones into the back of the VLA. That's not how it works. As much as I wish that's how it works, it doesn't. If you did plug in headphones, if they did have a nice little headphone jack back there, you wouldn't be able to hear what the VLA was hearing. Because we're observing at things like gigahertz, and I think the highest frequency humans can hear is like 20 kilohertz or something. So this is way, way, way beyond like the old analog TV sort of hiss that you used to hear when we were all young. But yeah, this is impossible. All right, so how do cataclysmic variables produce radio emission? That is my bread and butter. I love this stuff. So we're going to cover a couple different topics first. Bear with me. So here's my artist rendition of a cataclysmic variable again, and there are two different possibilities that we currently have. So in one case, we have a jet, and jets are one of those other ubiquitous kinds of processes in the universe. Jets occur in cataclysmic variables. They occur in different kinds of binary stars that have neutron stars and black holes. They also occur in big active galaxies with supermassive black holes at the center that are eating entire stars. As I learned recently, they even happen in forming stars too. So if you have a little baby star forming out of a big, big disk, it can send off wonderful jets as well. And all this is just a stream of material. So you have stuff from the accretion disk falling onto the white dwarf, and before it can actually hit, it gets redirected up into this stream of collimated stuff from the donor star. Now, the other possibility, the stuff that I study, of course, is this weird, bizarre thing called coherent plasma emission. And I know that sounds very dry and very boring, but trust me, it's very interesting. I love it. It's a process that could be present in the atmosphere of the donor star, or it could be generated somewhere near the white dwarf. And that's the thing that we're going to focus on today. If we were going to try to fit all of the different emission mechanisms here, I would be going way, 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 way over time. So before we move on, what I need to explain in this sentence right here is exactly what coherent means and what polarization means. Polarization might be very familiar to you if you have a pair of polarized sunglasses. The easiest way to explain polarization is with those, actually. So, you know, if you take them off and you turn them one way, you can't see reflections off the hood of a car. And if you turn them the other way, you can. And that is because the linearly polarized light is getting filtered out. So you can imagine that polarized sunglasses are basically like a fence. And depending on the orientation, different kinds of light can sort of sneak through the fence. But if it was oriented this way, they would just hit and not get through. So if we have a wave, a nice electromagnetic wave, we can just say, well, where's the electric field? It's kind of waving up and down over here. It must be polarized in this direction. We just choose the electric field as our direction. And so it may be tilted this way, it may be tilted the other way, but all in all, that is linear polarization. Now there's this weird, bizarre thing called circular polarization, where rather than just leaning over in one direction, the light is actually spinning. And it can either spin right or it can spin left. So those are the different types of polarization. Now, you can also have coherent light. Coherence is much easier to explain. So if we have two different waves and they're bouncing up and down together, this is in phase. Now, if they were slightly out of phase, they would not line up like this. And so when they're in phase, you end up with very intense, very highly polarized light. So in my case, for these coherent processes, we end up with very circularly polarized light. Now, the way you make all this stuff is you just need electrons flying around magnetic fields, because electrons are electrically charged. They want to gyrate around magnetic field lines. And there are lots of magnetic fields everywhere. We have one around the Earth, they're around the planets, they're in the sun. And so all of these things are sources of coherent emission. They generate auroral emission around the Earth. They generate auroral or decametric radiation around Jupiter. They're responsible for all the bright radio emission that we see from, well, not all of it, of course, but some of the brightest radio emission that we see from the sun. They're often associated with coronal mass ejections on the sun itself. And so this stuff is everywhere. It's not just in the solar system, though. It's everywhere else. The sun isn't the only star, of course, and other stars act quite like the sun. And so things like small red dwarf stars can do this too. And if we broaden our horizons a little bit and think about exoplanets, they should perhaps have aurora too. They interact with their stars, such that stuff from their star, like stuff from our sun, will eventually hit an exoplanet, or in our case, the Earth, and generate the aurora. So this stuff has direct implications for things like space weather around other stars, which I think is just bonkers, because we need to like study that stuff with the satellites around our planet. And this is an avenue to look at other exoplanets and how they might behave and have aurora, things like the northern lights here. But anyway, I'm getting all philosophical a little bit, so I have to move on. Hello. Oh, okay, good. Finally, on to my favorite stuff. So we're now going to talk about my research. We've got all of the prerequisites out of the way. So what we need to do now is talk about the best object ever in the world, QSVR. It is a pre-CV, that is pre-cataclysmic variable, because it's just not quite there. So when we have a cataclysmic variable, it's a donor star spilling matter onto the white dwarf. This is not quite there. It's just starting to do that. So it's just becoming a CV. Now, the first time this was detected at radio frequencies was with the VLA in the thing called the VLA Sky Survey. It's the most current survey that the VLA is undertaking, and it's going to cover the whole sky that it can see. Hello? Oh. Oh, I cut out there for a second. So when we saw that, we looked through the survey data and we saw this little dot where QSVR was. We said, aha, that's weird. We should take some pointed observations. So we decided, well, let's look from 2 gigahertz to 12 gigahertz. And we got 3 different observations. So one in 1 month, the next month, and another month after that. And basically what we were looking for was just highly polarized light, because that would be a key indicator of a coherent emission process. I think it's cutting out a little bit. Come on. There we go. Hopefully I'm not just destroying the micro. All right. So as I was saying, this is what we were looking for. We want high polarization. And so this is what we saw. Now, bear with me. I will explain everything that's going on here. So what we have on the y-axis is brightness, don't need to worry about this unit over here. It's fun though. You can ask me later. And on the x-axis, we have frequency. So from 2 to 12. And you don't need to worry about all of these frequencies up here. This is by and large uninteresting. Right here, though, is the cool stuff. So these data points up here are total brightness. It's slightly covered by me, RASC talking. Oh, this guy? Oh, yes, of course. Yeah, so right here, we have the 2 to 4 gigahertz data. Right up here is total brightness. So that's every photon that hit the VLA, regardless of its polarization. Now down here is a particular kind of polarization, the circular kind. And so these are just the photons that were circularly polarized. Now the negative numbers do have meaning. That is left. So what's spinning in one direction. And seeing that emission feature, we thought, ooh, that's bizarre. Why is it doing that? Because this is roughly, let's see, minus 400 to 800. That's roughly 50% polarization. That is a lot. Normally, you're going to get a couple percent at most. So we also looked at what was happening in time. So we split up the observation into things minute by minute. And so here we have a light curve, again, brightness on the y-axis, time on the x-axis this time. So this is all of the data in the 2 to 4 gigahertz bucket split up in time. So we start the observation and we don't see much. And then suddenly, at about 5 minutes in, we see this rise. This took about another 5 minutes to a peak, and then it starts to decline. And that corresponded with a polarization fraction of 68%. It was much higher than the one on the previous slide. So basically, what this seemed to indicate is something like coronal activity on the donor star. So remember how I said on the sun, this is associated with CMEs? That's coronal activity. So this might be something similar happening on the donor star itself. So now, before I move on to the next slide, I'm going to give you a little bit of an explanation. So each one of these data points is in itself a spectrum, its own little rainbow. And so I can take all of the data wrapped up into this data point and make a spectra from that in time. So I'll see the spectra at one point, then I'll see the spectra at another point. So sort of like on the previous slide here, instead of having this, which is all time, I'm going to split it up to see if there's anything that changes about the spectra. Does a peak rise here and disappear, or does it appear here? Because there is this big chunky thing here that I want to know more about. So that's what I did. So here, right here, we have funky words called Stokes I and Stokes V. These are the fancy terms that mathematicians use to describe polarization. But once again, it is just total brightness and circular polarization. So what I want you to focus on is 3 little points, actually, right here. So at the beginning of the observation, we have a flat spectrum, a flat little rainbow. And then at point 1, we start to see this rise that corresponds to the start of the rise in the previous light curve right here. This is this point. So it begins to brighten, then it reaches its maximum, and then it decays. And that corresponds with similar points over here. So the peak in, oh, my laser pointer is getting very dim. So the bottom peak on the right-hand panel corresponds with the bright peak on the left-hand panel. So there, what we're seeing is a significant polarization fraction consistent with something like 90 to 100%. And the bandwidth is roughly 500 megahertz. So this is narrowband enough and it's polarized enough for me to think, aha, I have a coherent emission process, because that's exactly what you want to see. You want to see something that is so unbelievably polarized that it can't be anything else. And that is where I'll leave you. So in summary, while this is going to work for QSFR. This isn't going to work for everything. Nothing, not everything has been observed as extensively as QSFR has. So we can only really say that this is indicating sort of where the research is going. More data like this, more broadband observations are necessary in order for us to understand what's happening in every kind of CV. Because right now there's very, very little data, and the data that we do have aren't very good. But at least for now, we know that QSFR is probably emitting some sort of coherent process due to this high circular polarization and that rapid time variability. Thank you very much.
Thank you, Margaret. Does anybody have any questions for our speaker? Alistair, right up front.
Very interesting. Thank you. What I was wondering is in terms of trying to differentiate between the red dwarf doing the emission or the disk doing the emission. On invisible light, we have blue shifting and red shifting.
Yeah.
Do you have enough resolution in radio to blue shift and red shift to see which component?
Very good question. So, the way you're going to differentiate between the two different objects is actually quite hard. I don't think it would be via blue shift or red shift, although you can see that in radio spectra. So let me back up a little bit. QSVR is an eclipsing system. So if you observe it for long enough, you will see the white dwarf disappear. And so if you see some big flare like what we saw, when the white dwarf is eclipsed, then you have your answer. But if you don't observe an eclipse, then it's a bit hard. However, you can observe red shifting or blue shifting in light, but that happens, it does happen from the Doppler shift effect. And that might be what we saw here. So if you look closely, those things that I've highlighted, the 1, 2, and 3 dots, they're shifting to lower and lower frequencies. That could be an indication that whatever thing is generating this light is moving away from us. Or it could also be that the thing is expanding, because sometimes the emission is actually tied to the density of whatever thing is doing the emitting. And so if it's expanding, the frequency will go down. Does that answer your question? Okay.
Any other question?
I love questions. Come on, you can ask about anything.
Anybody
Aliens.
online? Oh, Murray's got a question here.
Sure. The radio emission is generated by synchrone radiation from magnetic fields.
Good eye. So synchrotron emission is special. So we're almost at synchrotron, not quite. That's highly relativistic. So if you just have an electron zooming around a magnetic field, if it's non-relativistic, you can call it cyclotron. This is right in the middle. This is somewhat moderately relativistic sometimes, but this weird stuff right here. So most of this emission is moderately relativistic electrons. This weird emission right here is it's funky. If you have a big chunk of plasma, you need to be able to have a nice diffuse region, very highly magnetized region, to excite this thing called an instability. And that sort of it encourages the plasma to emit at these frequencies. It ends up causing the electrons to gyrate in phase with each other. And I think they are, for the most part, mildly relativistic at most. They're not super duper relativistic like synchrotron emission. What that comes from is something like a jet. So if material is falling into the white dwarf and then gets redirected in that collimated stream of matter, that's highly relativistic enough to generate synchrotron emission. And that's what we would, that's normally what is observed from jets coming from black holes, from neutron stars, that sort of thing.
Any other questions? Anybody online? No, sounds
Okay.
like you're good. Thank you very much, Margaret. We really enjoyed that presentation. Can we give her a round of applause for that presentation? Okay. Get Frank down here to do his wizardry work. Okay. Next thing on the agenda is a BNLL update by Luca Vanzella.
All right, so I have a BNLO announcement for everybody. Oh, I have to see my own screen though. All right, so early today I sent a message to the membership of the RASC Edmonton Center asking some questions. And they were, would you like to explore the universe with Western Canada's biggest telescope that the public can look through? And I should have added at a dark site. Or would you like to learn about the objects you can see as an amateur astronomer at such a place? Or would you like to discover how you too can use the RASC telescopes at the Black Nugget Lake Observatory? And if the answer to any of these questions for you is yes, then we have a special event for you on March the 1st out at Black Nugget Lake Observatory. And we're going to hold a workshop to basically go through these three things and let people that are not familiar with the site or the facility be able to learn about the telescopes there, learn about what you can see as an amateur astronomer in the night sky at a dark site, and discover how you can use the RASC telescopes at BNLO, the 32-inch Unit Drew telescope, the 18-inch Barry Arnold Memorial Telescope, and we'll also have a selection of one or more telescopes from the loaner program that people can borrow and use wherever they like, but also in particular at the dark site. So if you were interested in any of these, look in your inbox. You will have seen a message directing you to a site that describes the workshop where you can register. And in fact, we needed a minimum number of people to register for that. And in the first 3 hours this afternoon, in fact, we reached that threshold. So the workshop is definitely a go on March the 1st from 4 p.m. to 10:30 p.m. And this event, unlike workshop, unlike our event policy where we schedule with only very short-term notice in order to have high probability of clear skies, this one is scheduled. It's a few weeks from now, March the 1st, so of course it will be cloudy. But the workshop is a go because there's lots to learn about the facility and lots to do, even if the skies are cloudy. So we will have that. And in order to help us out with the clear skies, I would ask if there's anybody thinking about getting a new telescope the week leading up to that workshop, please defer your purchase or delivery of said telescope to increase the probability of clear skies on that Saturday night. So you don't have to be a member to attend this workshop, but I did give the membership first crack at it on Wednesday. If we still have spots open for the workshop, I will be putting it out on the Edmonton RASC Facebook group to let the 600 plus people that are on that group know about this workshop. So it's a go, and look forward to anybody that wants to learn about Black Nugget Lake Observatory. Register. It's free, and you can come on out. I will be here at the break. If anybody has questions, look for the blue jacket, and I can answer any questions you might have. Thanks.
Thanks, Luca. And as you said, he will be making himself available during the break, so that'll be great. Okay. Okay. So the next item is our trivia before the break, and you're going to have to work on that one a little bit. Okay, come on. There we go. 10 questions that you're going to need to come up with answers for. And actually, I did this on my own. I did not use a AI because I understand they're not actually smart as they think they are. So each one of these answers had been verified. So hopefully that the answers when you see them later in the evening will actually be right. We're hoping so. So in the meantime, I'm going to leave that up, and over the course of the break, you can see how many you can answer, and we'll take a look at that later on. Thank you. We'll take about 10 minutes. Okay, everybody, we're going to get back at her here. Give you a minute to get settled. Okay, I'm going to shut down the trivia, so I hope everybody had a chance to figure this out. And one of the announcements we're going to have is from a group that's going to be starting up the observers group again. So I believe, Alistair, you're going to lead the way on that?
Not on the trivia.
Or Murray Hunt?
Announcements.
Yeah, we're doing announcements. Yeah, there's a PowerPoint that goes with this. Yeah, so as some of you noticed, I was outside this evening in front of the Telus World of Silence. Woof. There's a Freudian slip for you. And showing crescent Venus through a small telescope. And hopefully I'll be doing a little bit of that before each meeting, as long as it's clear. Give people an extra little boo at the sky. Okay. On behalf of Murray Hunt and Berta Beltran, I'm part of the group that we are sort of reconfiguring, restarting, rekindling the observers group, and we want to focus on the beginners and those starting out, because all of the experts are already experts, and they don't need as much of group support as the beginners do. So we want to do something a little different, hopefully more eye to the eyepiece, things like setting up a telescope right outside the meeting, having a look, but also sort of almost ad hoc with 2 days notice. Hey, we're going to show up at the north side of the U of A farm, plop a scope down next to the nice double wide sidewalk where there's a bench, and we can have a look at stuff in the evening. Hopefully bring your own telescope so you can learn how to best use your telescope. So hopefully we'll be doing that. We'll be posting notices on Facebook and the Astro email listing for that. And also watch out for the cancellations, because of course things will be canceled as, oh shoot, too much cloud, that wasn't quite anticipated. So that will happen as well. But the other thing is, if it's a beautiful night, there's no guarantee that any of us are available to do one of these ad hoc eye-to-eyepiece sessions, because, hey, we all have lives too. So, but hopefully we'll get to look through a telescope a lot more often than sort of once a month. Oh, it's cloudy. Next month, oh, it's cloudy. Next month, oh, it's cloudy. So hopefully we'll get about that. Now, in terms of observing, what is there to observe? It's too cold. Fiddle faddle. It's not too cold. You can step outside for a minute and look up at the sky and observe. And part of that is watching the planets. Jupiter is starting to shift backwards into its normal direction, east against the stars, as Earth orbits the sun. And how we see that is you'll be looking up at Jupiter, Aldebaran to its lower right, the bright star Capella up to the upper left, and just watch how Jupiter goes from, not quite a straight line into a straight line to past a straight line. And before you know it, you go, oh yeah, I can, in the space of 3 days, just with my eyes, I can see that it's moved. Coming up a little later this month, Mercury is going to pop into the morning sky, and it's actually going to be a fair bit brighter than Saturn. as it comes in through the twilight, and will take a loop upwards towards where Venus is. Venus is going to appear to come down as the Earth's orbiting the sun will carry us around. But it appears to us that Mercury is going to go up, and Venus will sort of hang for a little while. And then, so watch for Mercury coming in on the 22nd, binoculars. That'll be the trick. And then a full month from now in a little bit, Mercury is going to be approaching us. It looks like it's looping away, but it's actually looping around and coming towards us on the inside track around the sun. And one of the things that is happening as Mercury goes through its phases from a gibbous disk into a crescent phase, it will be losing brightness because there's less and less surface for it to reflect. And so Mercury, by the time it hits its greatest elongation, best time to observe Mercury, it's already past its best time and it's fading. So just in the few days before greatest elongation and before it generally hits the news feeds, that'll be the time to see Mercury. And Mercury is actually pretty easy to see, not anywhere near as bright as Venus, not as bright as Jupiter, but still brighter at some points than Saturn has been in the evening sky. And then on March 1st, the crescent moon is in there too. So have a look at that. One thing I thought I'd address a little bit is the absolutely cringing AI art and talk about the planet alignment. And it's a non-alignment. And it's just like, where did this one come from? 13 planets. Well, it's obviously not our solar system, and it's sort of looks like our galaxy, but no, it's not even our galaxy either. Oh, yeah. So if you call up the Jet Propulsion Lab view of the solar system, this is what it really is like. And my next slide will show in larger font where the planets actually are. So in the center is the sun, Mercury at sort of 1 o'clock, Earth at 6 o'clock. And you can see Mars is at 7, Venus is at sort of 8 and a bit. You know, Jupiter's way off. It's just like there is no alignment there. But if you take any disc, whether if you're older like me, a vinyl record, or younger, a vinyl record, and you tilt it closer and closer to edge on, ta-da, a disc is a line. And so the planets are indeed lined up, but it's still, they're not in alignment, but they are lined up. And as the nice analogy that Bruce said, it's like it is a parade, but each of the planets are marching at their own beat, and they come by at different times. And so there's you'll see stuff about, oh, it's really unusual, rare, whatever, and it's like no, it's not particularly rare. It's very much harder to get the planets in order from Sun, Mercury, Venus, the Moon as an Earth substitute, Mars, Jupiter, Saturn. That's a bit tougher to get, less common, but just about every year you can go back on Astronomy Picture of the Day, year by year by year, and you can see these nice lines of planets in the sky. We're going to get one again next year. Well, this one is going to continue for a little while as Saturn sinks, Mercury pops up. So it's like, yes, the lineup of planets has been happening for the last 4 billion years and is going to continue every night for the next 4 billion years. But that said, that doesn't make it boring. It's still very beautiful. Walk outside, even if it's cold, and have a look. Just a couple of little announcements. On February 23rd, there's a citizen science workshop. See your national newsletter that is in your email, maybe in your spam folder, and to see details for that. One of the things that's happening next month, we'll do a little bit of, at the next meeting, talk about the total lunar eclipse. It's happening on a Thursday night. the eclipse itself is on the 14th, but not the evening of the 14th. It's on the evening or overnight on the 13th. So it's a Thursday night. After 11 o'clock is when the first dark bite is very noticeable. So hopefully we'll have something happening on the front lawn, and hopefully there's a lawn and not snow, but probably is a little bit of snow here at the Telus World of Science. We haven't had details yet, but we'll figure something out. It will be lawn on May the 3rd, unless there's a biannual Freak May snowstorm. And so we'll be doing International Astronomy Day on May the 3rd. So thank you very much for your attention, and we'll see you next month, and have a look on Facebook for any announcements of these semi-impromptu observing sessions.
Are you going to put anything up on the website as well? So also on the website, you can check on that as well. Okay, next up, we're going to bring up Mark Zelsick and Book of the Month. There you go, Mark.
Thank you. Good evening. Hello from the Lucian Campbell Library, which is located just off the entrance to the Star Theatre here. A big welcome to Rosemary Ball, who is the new co-librarian. Berta Beltran will still be putting the information on the Book of the Month on the center website each month. This month's Book of the Month is Carrying the Fire by Michael Collins. The book was recommended by David Halliwell. And indeed, the book came out originally in 1974, so it's been over 50 years since the first edition. Took a while for us to get the book, but eventually we got it. The years that have passed since Neil Armstrong, Buzz Aldrin, and Michael Collins piloted the Apollo 11 spacecraft to the moon in July 1969 have done nothing to diminish the fundamental wonder of the event. Reaching the moon remains one of the great technical and spiritual achievements of humankind. In this remarkable book, Michael Collins conveys in a very personal way the drama, beauty, and humor of that adventure. He also traces his life from his first flight experiences in the U.S. Air Force through his days as a test pilot to his Gemini 10 spacewalk, presenting an evocative picture of the joys of flight, as well as new perspectives on time, light, and movement as someone who has seen the fragile Earth from just above the surface of the moon. This book is available after the meeting. Thank you very much.
That is awesome. Thank you, Mark. That's I really have to thank Jeff for that, because Jeff was the one that mentioned this book, and I was so excited. So I'll make sure I'm in attendance next month, and if it's still there, I'll be the first one to jump on it. Thanks.
Thanks, Mark. Okay, next up we have Tom Owen, who's going to present the Astral Imaging Corner to us. So I'm stopping my share. So whenever you're ready, Tom.
Thanks very much, Clayton. I'm going to see if I can share my screen now. Okay, can we see that?
Hang on.
I can see it online.
It looks like you're there, almost there. Hang on.
Okay, so everyone can see that?
Yep.
Okay, well, I'd like to welcome everybody to the 143rd edition of Astro Imaging Corner. I'm grateful to my predecessors, Massimo Tori and Abdur Anwar, for so capably carrying on the tradition, and I'll do my best to live up to their great work. There we go. So I thought I would start with some commonly used terms for people who may be unfamiliar with the jargon of astrophotography. And so these are not by no means this is comprehensive, but just a few that I thought I should to try to explain. So you may hear references to subs. Those are individual short exposures. Stacking is the process of combining subs to increase detail and reduce noise. And noise, well, it's the visual equivalent of the static you hear in your car radio when you're in Edmonton, but you're trying to listen to a Blue Jays game on a Calgary radio station. if you know what I mean. And that gives a grainy look to pictures. And then we have the abbreviations LRGB, HA02, S3. Those are abbreviations of the names of filters that are used in mono cameras. You may hear reference to NGC. NGC is the new general catalog of nebulae and clusters of stars, which is compiled by a fellow by the name of Dreyer in 1888, and he was supplementing the early works of the Herschel family. And then IC is short for the index catalogs, and these were two supplements to the NGC catalog, also published by Dreyer. Now, the first image we have is by Alistair. It's an asteroid occultation, and you can see it's a video. I know Alistair is there. Alistair, I could read the blurb that you sent to me, or you could just come up and talk about it. What do you want to do?
Here we go. So near the center, just left of center, this is a loop. So you'll see a star that sits there, it's gone, and then boom, it's back again. This is what happens when, some people using the Jet Propulsion Lab information do a forecast of asteroids in the asteroid belt passing in front of stars. And they can do this accurately enough to figure out where you need to be on the planet to see these things. And just about any average spot can get one of these about once a month or so, depending on the brightness. There was one earlier this evening which had a lower probability, so I didn't worry about chasing it. So you'll be seeing a lot more of these coming from me over the next year or so. But they're kind of fun. You can even do these visually at the telescope. Say this was an 11th magnitude star, so not that much of a trouble for a C8, even from the city. As you can see from the time below, often these things last only a second or so. And a second is a long time with the eye at a telescope. And so you can join in just to have a look. And I'll be publishing those on Facebook if we get a really nice one across the city.
Terrific.
Okay.
Yeah, I think that's just remarkable, Alistair. And thanks for sharing that with us. It's really great. Now we've got an image from Josephine, the Rosette Nebula, and it was taken January 27th, 2025, and she's using the framing and mosaic mode on a C-star S50, an hour and 18 minutes of 10-second exposure. So folks, this is what you can do with a 10-second exposure. The pic was edited in Photoshop Express and Lightroom, and she also used the AI denoise feature from the C-Star S50, and she says it was only cropped a bit. So, Josephine is an experienced terrestrial photographer, I can put it that way. And I want to say that this image, even though she's a novice at astrophotography, this shows some real maturity in how it was put together. So well done. This is her Bubble Nebula. It was taken September 8th, 2024 at the Northern Prairie Star Party, again with the C-Star S50. And it was 71 minutes of 10-second exposures. And again, it was edited in the Photoshop Express app and the Lightroom app. No AI denoise was used in this one. She says it hadn't been updated yet. Now, this is a fellow by the name of Zeidler. He's been a member for some time. This is, of course, M42. He said that this image was taken with the club's C-Star S50. He said there's only 10 minutes worth of data as December was quite cloudy, and we all know that. This is his image of the total eclipse of April 2024, taken from Texas, from Dallas in particular. And he says, we got lucky and it was pretty clear for totality. So very nice image. This is an image from Craig Sherris. This is the fossil footprint nebula NGC 1491, 17.4 hours of exposure. And he says, the fossil footprint nebula, also known as NGC 1491, is a captivating emission nebula located approximately 9,800 to 10,700 light years away in the constellation Perseus, on the edge of the Perseus arm of the Milky Way. This nebula is notable for its vibrant red coloration, which is as a result of the ionization of hydrogen gas by massive stars embedded within it. This is a stellar taken with a stellar view SVX 130TR and a Poseidon C Pro camera. And I was thinking about this, you know, we like to give cutesy nicknames to deep sky objects, which I really don't like. But there's nothing cutesy about this nebula, is there? I mean, this is a powerful image of a roiling gas cloud, and I just think he's captured it. It's very, very powerful. So well done. This is my image of NGC 2174, aka the Monkey Head Nebula, and I was very determined when I was processing this not to make it look like a monkey head. It's a diffuse nebula surrounding the open cluster NGC 2175, and it's located in Orion. I imaged this in Palm Springs last November 20th with a 90mm triplet refractor using HA03 and S2 filters in a QSI 683 camera. It only represents 95 minutes of total exposure using 5-minute subs. It's a strongly emitting nebula, so it's not really necessary to have too many hours of exposure to produce a decent image. Subs are stacked with AstroPixel processor and processed using star tools. And this is my image of the lunar halo, which occurred on February 7th. I took this out at Pigeon Lake and simply pointed my cell phone up, put it on night mode, held it for a count of 4, and this was what was produced. It was taken outside our cabin, which is known as Moondance. That's Jupiter on the right, Capella on top, Mars on the left, and Betelgeuse on the bottom. And that's a contrail underneath it. I want to say that when I was looking up with the naked eye, I mean, I could make out the image, the halo very brightly, the stars very brightly, and the moon was in perfect focus. It wasn't blown out. And it's, again, a demonstration that the dynamic range of the human eye is something to behold, and it's certainly better than any cell phone camera. This is from Hans, and this is IC443, the Jellyfish Nebula. It was taken with a Teleview NP127IS and a 0.8x reducer for a focal length of 528mm at f4.2. Subframes were acquired with the ZWO ASI 2600 MC Pro camera. Filters were 4nm dual narrowband HA03 and S203 from Altair Astro. The total exposure time was 21 hours in narrowband. And stars were added in RGB for a total of a 1-hour exposure with the RGB stars. Acquisition software was Nina, and processing was done in PixInsight. Processing wasn't as straightforward as I'd hoped because the O3 signal was surprisingly weak, he says, perhaps because of the full moon on some of those nights. And he says the Hubble palette didn't give good results, so I modified it and used HA for red and mixed O2 and S2 for green and blue. And this is, Hans, this is one of the best images of the Jellyfish Nebula, and God knows it's a popular subject. This is one of the best images I've ever seen, so well done. This is, of course, the IC 1805, aka the Heart Nebula. Equipment and software were identical, he says, to IC 443, but the narrowband exposure time was shorter, 13.5 hours. And this is processed in the SHO Hubble palette. So again, for people who don't know, when the images come from back from Hubble, they're in black and white. And so color is applied to them. And then the so-called Hubble palette is used, which is identified with the images from that telescope, where S is mapped to red, H to green, and O to blue. Great job there. This is from Dave Mussel. It's the Pac-Man Nebula NGC 281. He also gives it the name of the Eye of Sauron. It's found in the constellation Cassiopeia, about 9,200 light years from Earth. It's a large diffuse nebula composed of mainly ionized hydrogen gas. It contains Bok globules, which are dark, dense regions of gas and dust associated with star formation. The image was taken with a 5-inch refractor fitted with a monochrome QHY camera and a filter wheel. It consists of a total of 7.5 hours of integration time from 2 nights of imaging in December. And I really like this image. I love the intensity of the color and the great detail in the, I suppose there are dark nebula. Really great detail. So good job, Dave. This is from Ray Weens. It's the Flaming Star Nebula. And I'll be showing you Thor's helmet as well. He says both were taken with the QHY 286C camera attached to a WO, that's William Optics 132 millimeter, mounted on Ioptron CEM60 mount. The Flaming Star Nebula is 18 images, 18 subs or images at 300 seconds each, and processed in Lightroom. And the runaway star is that bright star, which you can see sort of in the top center of it, left center of the image, and it's firing up and illuminating all the gases. It's a runaway star, and it's running away, and it's lighting up this gas as it proceeds its way. And this is Thor's helmet. It's in Canis Major. He says this is 9 subs of 300 seconds each. It was processed in Lightroom, and this image is low on the horizon, so it meant dodging the trees at the Blackfoot dark sky site. I was pleased to get 45 minutes in, and I tip my hat to anybody who can image Thor's helmet at our latitude. So this is an image from Tim and Jason Badry. It's the moon, February 7th. And they are new members. And I contacted them over the weekend in my role as membership secretary. And I'm just going to read you the email that I got from Jason and then how this image came about. So Jason says, I was a member for a year, maybe 10 years ago. But at the time, it wasn't quite a fit. My primary hobby has always been photography, and perhaps it was a bit early then to mix the two. Now, though, we are quite into astrophotography and have geared up a lot in the past year with a couple of mounts, astro cameras, ASI Air, etc. My younger son, Tim, has shown a lot of interest and did astronomy 10, 20, and 30 at Jasper Place, also being one of the student presenters at the last meeting. Zach is just starting NATE in computer engineering / technology, but doing night classes right now, so won't be able to join much this year. My background is IT infrastructure, and so I like the technical aspect of this, figuring out how to use the gear to get the photo. I like to encourage the boys with science / technical stuff. We are often at the twos for events and have IMAX passes. Attached is Tim's latest from the weekend. We took some 8K video with my camera / lens, and he stacked it. He wants to try that next with our refractor and the camera. So I want to say welcome to the Badries on behalf of all of us here at the club, and great image. I really, really, really like that image, and I look forward to seeing more images as well. I know they're online, so like I said, welcome from everyone. And that is almost the end of my presentation. So please send your images to astroimagingcorner@edmontonrasc.com. I would appreciate it if if the images didn't come in on a Saturday night or a Sunday before the meeting. And then I would have a little more time to devote to putting everything together. But I do appreciate all of the interest and all of the wonderful images. Really enjoyed today's presentation because it shows that there's a whole range of skills in the cloud, from novice to experienced imagers. And everybody, I just say, just keep climbing that ladder. It's just going to keep getting better and better. So thank you very much. That's my presentation tonight.
Thanks, Tom. We welcome the battery to the RASC Edmonton Center. That was a fabulous photo of the moon. We're in the home stretch. So now, from our big trivia, we'll go to the answers here now. So on the first one, that was pretty straightforward. National Aeronautical Space Administration. But I figured that when Elon Musk gets in charge of that, it's going to become SpaceX. What is the name of the low-level microwave? Radiation, cosmic microwave background. First woman in space. Did anybody not get this one? Valentina Tereshkova. And we had the tidal locking, when the satellite takes exactly the same time to rotate as it does to complete an orbit. Fastest space probe is the Parker Solar Probe that's currently running around the sun at the moment, getting some fantastic data. The TARDIS project sent what kind of animal into space to see if it could survive the extreme conditions? Tardigrade. They're a microscopic insect, I guess. If you ever saw one in a picture, you would swear it came from a science fiction movie as an alien. The visible surface of the sun is the photosphere. What is the only large moon in our solar system that orbits in the opposite direction of the planet's rotation? That's Triton around Neptune. Due to dust in the Martian atmosphere, what color do the sunsets appear? And blue is the answer. And what theory posits the universe will end by collapsing in on itself when its own gravity overwhelms the power of expansion? Opposite of the Big Bang, we have the Big Crunch. I don't know how many people got 10 out of 10. When I first did it, I only got 8 out of 10. So. Okay, final announcement. Just again, the Astroperic member perk, if you're interested in taking a look at that, getting it on your computers. If you like access, you download the app, send a request to join the RASC Edmonton Center group, and you must have an email associated with your RASC membership. You got all the information from Alistair early on about the observers meeting. So I won't go, we don't need to go into that. Our next monthly meeting is on Monday, March the 10th, again, starting at 7:30 Mountain Time. And I'm introducing a new feature every month called the Cartoon of the Month. So if you have a cartoon you would like to send in to me to put up during the presentation, just email it to president@RASC or edmontonrasc.com, and we will select every month, put 1 or 2 cartoons up. So for this month, I got one off my fridge. It's been up on the fridge for a long time. Tomorrow will be clear and sunny, with vertical visibility being 193 million miles, increasing to several hundred light years at night. Well, that was the weather forecast back in that day. So if anybody has anything they want to cartoon to send in, let me know. Our next meeting will be March 10th, next month. So thank you for attending tonight, and I will call the meeting to adjourn.